Good day, dear pharmacist. How are you? This is our first lecture, and in that lecture, we will mainly discuss the introduction to chemistry. And that lecture, we will discuss the definition, types of organic and pharmaceutical compounds, nomenclature, the hydrocarbons, aliphatic and aromatics. Also, we will discuss the functional groups, types of aliphatic hydrocarbons, and at the end, we will be discussing the most important thing, which is the stereochemistry. Okay, so let's start. First of all, we will go for the definition of the pharmaceutically active compounds. So we have here initially, we will go for the definition. It is the study of compounds containing nitrogen, oxygen, carbon, and hydrogen, which is considered to be the essential atoms in the organic compounds. So those are the most important atoms in the compound. We will have carbon, hydrogen, oxygen, and nitrogen. So mainly we have here two types of the pharmaceutically active compounds, the aliphatic compounds and the aromatic compounds. Okay, so what's the difference between the first and the second one? The aliphatic compounds, as you see in the note, those are hydrocarbon, which is carbon, hydrogen, joined together in a straight chain or branched chain. Okay, so this is the definition of the aliphatic hydrocarbons. Straight chain. Okay, so for the aliphatic hydrocarbons, it is illustrated into two main types. The first one, which is the detailed, and the second one, which is the summarized, or you can say that. This is an example for the summarized structure, where each angle represents a carbon atom. Okay, so for example, at that compound, we see now we have 6 carbons. Okay, and there is also the attached hydrogen atoms to it. Each carbon form 4 bonds, either single or double or triple bond. Uh, so here we have the hydrogen, for example, and this is the detailed structure at the right, and at the left we have the summarized structure, which we mainly use to save time. Okay, so as I told you, the carbon atom has 4 bonds. It can be single bonded or double bonded. Okay, like that, or triple bonded like that. Okay, so this is the structure and the main bonds that can be formed by the carbon atom. So if we have single bonded aliphatic hydrocarbon, this is called alkane. Okay, we will discuss that in details after that. So we have alkane. Sorry. If it is double bonded, it's called alkene. If it is triple bonded, it's called alkyne. Okay, so this is the This is the types of the aliphatic hydrocarbons. تمام. alkan, alkene, alkyne, alkane single bond, alkene double bond, alkyne triple bond. Thank you. Let's continue now. We have then the aromatic hydrocarbons. Aromatic are cyclic unsaturated structure. This is the cyclic unsaturated structure. Also, as you see in the notes in front of you, there is three types, the detailed and the summarized structures. This is the common structure we use for the benzene ring. As I told you, the aromatic structure is a ring of unsaturated carbon atoms, cyclic unsaturated carbon atoms. Also, we have that structure. It's a detailed, has some details here. The structure has some details here. Here's double bond, single bond, double bond, single bond, and so on. Or the detailed structure, which is time consuming. We will draw six membered ring benzene with all its bonds and carbons, hydrogens like this. And in each there is a hydrogen atom here, 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 and here, as you see. Okay, so all the three here are the same, but we mainly use that one because it's easy and time saving. That's in terms of the types and classification of the pharmaceutical compound, and also in general the aromatic compounds. Now we will go for the nomenclature. Nomenclature. How can we give a name to a compound? There is, first we need to know the corresponding name for the number of carbon atoms. So as you see in the table, we have here one carbon atom which has the name of takes meth, two carbon atoms takes eth, three carbon atoms takes the name prob, four carbon atoms takes the name but, five takes pent, and six hex. Of course, there is other names for 7, 8, 9, 10, 11, but we mainly use those six in the exam. So the six carbons we have, I have not seen in the exam that we have used other than six. Less than six, yes, we can find in the exam, but more than six, I have not seen that. So what we do, we will draw three lines for the nomenclature, or the process of giving a name to a pharmaceutical compound or an organic compound. Here at the middle, we will add the parent chain. We will add the parent chain. Parent. That's the one. Here, the suffix, which represents mainly the functional group. the first part, which is the substitution. Okay, so this is the suffix and here the substitution. This is the very important. So what we do, for example, we have that structure. Okay, we have that structure. First of all, the first step, number one, we will calculate the number of the carbon atoms, which is represented or presented in the molecule or the compound. We have 1, 2, 3, 4, 5, and 6. Okay, now we have 6 carbon atoms, so 6 it will be hex. So first here we will add hex. First one. After that, do we have a single bond or double bond or triple bond? Here it is straight unsaturated. Unsaturated means that there is no single or double bond. So it is alkane. It is alkane as there is no double bond or single bond. As I told you before, we have alkane, alkene, alkyne just 1 minute ago. Alkane, single bond, alkene, double bond, alkyne, triple bond. So we have here no bonds, so it will be alkane. So we will add N at the end as a representation of the unsaturated carbon chain. If we have a double bond, we will add in, so it will be hexene. If we have a triple bond, it will be hexyne, YNE. Okay, so this is the first thing which we counted, the parent chain in the middle. Then we will add a suffix which represents the functional groups. The functional groups, as we all know, alcohol, ketone, carboxylic acid, aldehyde, ether, ester, amide, amine. All of these are considered to be a suffix, functional groups for the compound. Here we don't have, so we will leave it blank. After that, we will go for the substitution. Number one, here, the substitution. We will add we have here a substitution, which is the iodine. That substitution could be a methyl group, an ethyl group, iodine, bromine, chloro, any type of substitution that is already present on the carbon chain. At that example, we have an iodine. So we will add the substitution. We will write first the number and then we will add the name of the substitution. So here we have 5 iodo. Iodo means iodine. If it is chloride, it will be chloro. Okay? Is that correct? No, it's not. Why it's not correct? Because here the substitution has to take the lowest number. Lowest number. Meaning, if I count from the right, somebody will count from the left. It will be 1, 2, 3 carbon atoms, 4, 5, and last one is 6 here. Okay, so we will count the carbon chain in a way that we give the lowest number for the substitution. Okay, so now if we count from the left side, we will have the substitution of 2-iodohexane. Okay, iodohexane. So which one is correct? That one. Okay, I have mentioned that, so the information stick in your mind to pay attention to it. Okay, so this is the most important thing, that we give the lowest number to the substitution we have. Okay, so let's have another example so it will be more easier. Let's clear all. Okay, we will do our steps here: substitution, parent carbon chain, and suffix. Okay, for example, we have 1, 2, 3, 4. Okay, we have here, for example, as CH3. So we will start counting to give the substitution the lowest number. 1, 2, 3, and 4. If we count from this right side, the methyl group will take the number of 3, which is not correct. We will count from here so we can give the substitution the lowest number. So where's the longest? Also, we have here a very important note, which is where is first? The first thing we do, the longest carbon chain. Which one is the longest carbon chain here? 1, 2, 3, and 4, and 1, 2, 3, and 4. So it is the same. So we can count and consider that one to be the carbon chain we have as a side group. So we have 1, 2, 3, 4. 4 corresponds to bute. So we will write bute. All single bonds, so it will be N, butane. We have no functional groups, so there will be nothing after the butane, and the substitution is at the carbon number 2, and the type of substitution is methyl. That's it, 2-methyl butane. It's easy. Okay, let's now clear all and proceed. That's good. So as to summarize that point, which is very important, we calculate and identify the longest carbon chain. We add the name for the carbon chain. We determine if it is alkane, alkene, alkyne. Then we determine the number, the the position of the substitution, and we give it the proper, the lowest number, so we can get the information from. Now I will show you two example from the exam. Okay, now we will have two example from the exam. The first one, as you can see on your notes, please count. Sorry, we will count now. 1, 2, 3, 4, and there is an OH here. And here is chloro. 3, 2, 3. Okay, so as we say, we need to give the lowest number for the functional group and the substitution. If we count from here, we will have, from the left I mean, we will have a substitution number 3 and an alcohol on 5. However, if we count from the right, we will have carbon 1, 2, 3 chloro, 4 and 5 5. Okay, so anyway, we will draw our three parts. Longest carbon chain, we have 5, 5, which is, yes, pentan, that's correct. So pentan, no double bond, no triple bond, so an, as it is alkane. We have here a functional group, okay, so it will be all, as we will take the abbreviations for the functional groups. So the suffix here is all because we have a functional group, which is the OH. Anyway, now the substitution we have also on carbon number 3 for chloro. Okay, chloro, so 3 chloropentanol. This is the correct nomenclature for that. On the other hand, now we have a structure and he gives you a multiple choice to choose the correct one. The question came in the exam for propan 2-ol. Propan 2-ol. We will do the same now. Prop, which means 1, 2, 3. 1, 2, 3 carbons. 2 here, ol, which is the hydroxy group. That's it. Group N, there is no double bonds, so it is N, and functional groups, which is all. Okay, so this is the correct answer. Also, you may find it in the exam. This is why we draw the detailed structure. This is the summarized one, so we can draw faster and save time. And this is the detailed structure. Okay, so 1, 2, 3, no double bonds, as it is N, ol 2 ol, so this is the hydroxy, and the hydrogen atoms distribution will be like that. Okay, so let's continue now. Also, we have here, sorry, clear all? Yes, thank you. Now we will go for the aromatic hydrocarbons. The aromatic hydrocarbons, as we see from the definition before, which is cyclic unsaturated carbon atoms. So this is the carbon atom. Sorry, this is the benzene ring. For example, we will have the functional group here. We have 1, 2, 3, 4, 5, and 6. So if we have the substitution between, I will show you something before we do that one. Okay, so this is the name for the substitution. Okay, this is the functional group here. Those two carbons at the side of the functional group, so it is called ortho. Ortho. Okay, ortho. For that one and that one, it's called the ortho substitution. At that two positions, it is meta. Okay, meta. And at the opposite direction of the functional group, it's called para. That's it. Also, it's called, if it is 1 and 2 substitution, this is the one carbon, as you can see here, 1 and 2 substitution, it is ortho. If it is 1, 3, it is meta. If it is 1, 4, it is a para substitution. Okay, this is an exam question, by the way, so you can be aware of that, because it's very important here that to determine the positions of substitution on the carbon ring. 1 and 2, it's ortho. 1 and 3, it is meta. 1 and 4, it is the para. Okay, so let's continue. Now we will have an example for the nomenclature. Those two examples came in the exam. The first one, which is that one, what's the name for that molecule? It is called phenol. Okay, it is called phenol. It's very well-known compound. So let's go for the second one, which is that one. This is the OH here, and we have chloro at that position. So the name for the compound itself, as we see before, it is phenol. So we will write here phenol. The substitution will be on the left, as we have learned from before. So the substitution comes before the name of the compound. So the name of the compound is phenol. So the substitution comes before it. We have here chloro. We have a chloro. Chlorophenol. So, but we have here an issue. The chloro, this does, if I see chlorophenol, I don't know whether it is here, here, here. Where is the chloro? So this is why they have added metachlorophenol. That one is called metachlorophenol. Okay, this is a very simple way to name the cyclic aromatic compounds. Now, we will go for the functional groups. Please, if you are with me now, please, I want you to take a 5 minutes rest, pause the video, and we will continue after 5 to 10 minutes so you get refreshed and to be ready to absorb the new information, which is very important. Thank you for that. Now we will start the second part of the our lecture, which is related to the functional groups and the stereochemistry. This is the very important part you will face in the exam, and also there is a very important basics that we will establish at that part, which will help us in future, and I will show you in a minute. Okay, so now as you can see from the notes you have in your hand, we have the first thing, which is the alkane, alkene, and alkyne, as I told you, which represents the number of, it's an indication of saturation and number of bonds that the carbon atom is linked to. So what is the structure for the alkane? Alkane, which is saturated hydrocarbons. By the way, the presence of the double bond or triple bond gives reactivity, also instability. If we have a molecule that is a double bonded or triple bonded, that means it is unstable and it is reactive. That molecule is reactive. We cannot see that in the alkanes. Simply why? Because we have only single bonded compound. So we have a character here, which is that the molecule is stable. The saturated hydrocarbons are stable and water insoluble. Water insoluble. Now let's see why and what is the importance of water solubility at that particular part in the compound. Why? Why, by the way, why is the door, it's the gate for your knowledge. It will save a lot of time in the process of studying and saving information in your mind. Before we do that, as we all know, the water solubility will help us in the pharmaceutics part, so I need you to understand that part very, very well. We have here, this is the molecule of water. That one is a negatively charged and that one is positively charged. And it is ionized. That compound is ionized. Okay, so the presence of the atoms in the water, it will be with a charge, which means that we have a polar structure here. Okay, polar. Part of it which is negative, part of it which is positive. Okay, that's very important because here the alkanes are hydrocarbons that are non-polar. It is non-polar, and the water molecule is polar, so they are not mixed together. We cannot mix that as if you are mixing oil and water. It will not be mixed together. Why? Because there is no polarity in the hydrocarbons, so it will not be mixed with the water. It will not be soluble in water in another way. Let's go for the alkene. The alkene and alkyne. The alkene and alkyne are, it is unsaturated, as we have said before, due to the presence of double bond or triple bond. It is water insoluble. There is no polarity. It is non-polar also. How can we gain polarity? By the presence of H or OH or oxygen alone, and I will show you now that what that means. Okay, so as I told you, the presence of double or triple bond cause instability, activity, and reactivity of the molecule. That means that this double bond is very active and tends to break and form a new bond with the other molecules. For example, it can form a hydrogen bond by the process of hydrogenation, or a oxygen can come at that part and form an epoxide. This is all an example. It's not an important in the exam, but just I'm showing you how that part, the double bond, which is reactive, and they can form a new bonds, tend to form a new bond. So that's why it is reactive. While the alkane is non-reactive because the presence of single bond caused the stability and cause the molecule to be not active. Okay. Now we will go to we have discussed the alkene, why they are water insoluble, because they are non-polar. Now we will go for the alcohol. The alcohol is a very, very good example to what we are now going to discuss. Thank you. What's the sample the for the alcohol? That's we can say the molecule, the general molecule for the alcohol. That's the one, where R represents a number, any number of carbons from 1 to 100 or 200 carbon atoms. It can be any of them. But let's check the presence of OH here. That means that this molecule, this compound, is alcohol. This is the first one. At the nomenclature process, it takes all at the end of the molecule, as we have discussed. This is the part, that part for the nomenclature. It takes OL in the nomenclature process, as we have seen in the example I have shown you before. Another important thing, if I ask you, is that compound is water soluble or lipid soluble? That that compound here, we have two parts in it. The first one, which is the OH part, that part adds polarity to the molecule due to the presence of oxygen and hydrogen. That polar size causes it to be water soluble. Excellent. That's correct. So that will cause water solubility to the molecule, the presence of OH. However, the other part of the molecule will cause the molecule or the compound to be lipid soluble due to the absence of the polarity at that part. So that part will cause the molecule to be lipid soluble. That part will cause the molecule to be water soluble. That's good. Also, there is a very important thing. We will discuss it after that, not at the time. Now, if we want to mention some important parts and topics in relation to the exam, alcohols can form a hydrogen bond. Alcohols can form a hydrogen bond. Hydrogen bond, so that's why it is water soluble. Something also which is very important, that alcohol, glycerol, can considered to be alcohol also. Glycerol considered to be an alcohol. Now, in terms of those two parts which represents the exam questions, that one is an exam question. Why or what type of bond that's formed between alcohol and water? It is hydrogen bond. The presence of the hydrogen bond, the presence of polarity on the alcohol molecule cause it to be polar water soluble. The other part of the molecule, which it's non-polar, so it causes the molecule to be lipid soluble. We have three types of the alcohol. The first one, second one, third one. The first one, which is the primary alcohol. The primary alcohol. Okay, just a second. This is the primary alcohol here, which is RCH2OH. This is the example of the primary alcohol. That one, when it is oxidized, it gives me aldehyde. When we oxidize that molecule, it gives me aldehyde, which is CHO. R. Okay, that one, which means aldehyde. Okay, so the oxidation of primary alcohol gives aldehyde. Secondary alcohol, what's the meaning of secondary alcohol? Which there is a branch here of, for example, CH3. Okay, means that the OH in the middle of the molecule, or not at terminal part of the molecule. Okay, so the oxidation of that one, the secondary alcohol, gives ketone CO. Okay, this is the secondary alcohol. The tertiary alcohol, it is not oxidized. It is very, very stable. We find here R, and okay, that one non-oxidized. By the way, all of those three are exam questions, so beware to know that. Well, we have here 5 exam questions: hydrogen bonding, type of glycerol, the oxidation of alcohol. Okay, now just to emphasize the importance of polarity and water solubility, and as I told you, in the lecture of each class of medications, we will discuss the molecule and that class of medication in terms of chemistry and pharmacology. We will show the relation between the chemical structure and the reactivity and biological effect of the molecule. So that one, the solubility will help us too much. Now we have the ether using our previous rule. Using the previous rule, we have here two parts of the lipid soluble part and oxygen, which is mostly causing the molecule to be polar, or part of the molecule to be polar. So it is partially soluble. Why? Because it is surrounded also with not a terminal group like the OH. We cause the molecule to be water soluble, but here it is partially water soluble because the polarity is in the middle of the molecule. Okay, so the ether is lipid soluble, two groups of nonpolar, and partially soluble due to the presence of oxygen. Let's go to the aldehyde. It is the same. We have here CHO. If the R, which is representation to the number, any number, as I told you before, of hydrocarbons, is very high, meaning it is 30 or 20 carbon atoms, that will cause that molecule to be more water soluble because the fraction that is nonpolar is more powerful in its effect of on solubility than the terminal part, which only has one oxygen. So as we see, as the molecular weight decrease, meaning low number of carbons on the R, that means that gives water solubility. That will be in the favor of the oxygen, the hydrogen and oxygen at the terminal. By the way, not to misunderstand that molecular formula, that structure is like that. Okay, this is the detailed structure. Okay, so not you misunderstand it or be confused with the alcohol, which is like this. It's totally different. Both of them are OH, but however, the OH in the alcohol is different than the aldehyde, which is that one. That's the aldehyde. Okay. So this is in terms of the water solubility. One exams comes at that part, which is the polymerization of aldehyde give paraldehyde gives para. So this is the paraldehyde. And also at the end of the lecture, I need you to check and search for the paraldehyde structure. Okay. After that, the amines. The amines, which is mostly NH group. Okay. So we have primary amine, secondary amine, tertiary amine, and quaternary amine. Quaternary amine, it is a positive charge. It is a positive charged molecule. Okay, it will be CH2 N 3, meaning that we have 3 molecules here and it is positively charged. Okay, the other, this is the tertiary, the quaternary, the tertiary will be N R R CH2. This is the quaternary, tertiary. The secondary, here we have H2, here in H and R. So to summarize that part to be more easier for you to understand, primary amine, we have nitrogen with 2 hydrogens. Secondary amine, we have nitrogen with 1 hydrogen. We replace 1 hydrogen with an alkyl group. Okay. Tertiary, we remove both of the hydrogens, substitute it with the two alkyl groups. Okay, that's it. So this is the amine. The amines are mostly basic in nature. As we go down the quaternary amine is more basic, and this first one, which is the primary amine, less basic. Okay, that one is less basic. Also, the same rule for solubility. As the number of R increase, that gives lipid solubility, and if it is low number of the alkyl group here, meaning, for example, CH3, CH in H2 or 3 or if any, it will be more water soluble. As we have low number of carbons, that means more water soluble. If we have high number of carbons at the alkyl group here, it will gives me low water solubility, high lipid solubility. Okay. Okay. Now we will go for the carboxylic acid. It's very important to know that the carboxylic acid, which are C O O H. This is the carboxylic group. It is acidic in nature, water soluble. We have that structure as we can see here. That one, those one cause polarity, water solubility. As the number of carbons in the alkyl group increase, the water solubility increase. If it is low number, the alkyl group, it is more water soluble. The reactions, we have one of the most important reaction, okay, which is the saponification reaction and esterification. Saponification, if the carboxylic acid or the fatty acids or the triglyceride reacted with a strong inorganic base, which like the sodium hydroxide or potassium hydroxide. Okay, so sodium hydroxide or potassium hydroxide with the fatty acid, organic acid, or the triglyceride, that will give me soap plus glycerol. Okay, soap plus glycerol. And that one is an exam question, by the way. Okay, that's one considered to be very important because mostly you will face that exam in the question. That question in the exam, sorry. The other thing, which is the esterification, if the carboxylic acid reacted with alcohol, it gives me an ester. Okay, and the ester and water, and that reaction, it's called esterification, and it is forward backward reaction, meaning if I that means if I have an ester and I add a water to it, that will cause me the reaction to go on the backward to give me an acetic acid and an alcohol. Let's remove all of those ones. Everything is good. we have seen and discussed the ketone CO, and if you are clever to remember that ketone is a reaction of, yes, correct, it is a reaction between secondary alcohol. The oxidation of secondary alcohols give me a ketone. That's correct. The exam questions comes at that part, which is the camphor considered to be a ketone. So camphor is a ketone. Okay, and we have also the same rule applies to solubility, and we have discussed the ester as I told you before. Now we come to the most important thing, most important part, which is an exam question. You may find here 2 to 3 questions minimum in the exam, the stereochemistry part. Okay, so the first thing, if I give you a molecule which is CH3H6O, this is called the molecular formula. I want you to check for that molecule, for that compound, draw a structure to that one. Okay, just draw a structure to that compound. Okay, so me as Islam, I will draw it like this. For example, sorry, just a second. It will be like this. Okay, so I draw it like this. We have 2 carbons. Sorry. Sorry for that. 1, 2, 3, 4, 5. Sorry, it will be C2. Okay. If we would like to have a structure C2H6O. So we have that structure. I drew that structure. How many carbons? We have 2. How many oxygen? We have 1. How many hydrogens? We have 6. 1, 2, 3, 4, 5, 6. That's correct. It's 100% correct. And that molecule is an alcohol. For sure, it's an alcohol. Somebody, another friend, will draw it like this. C O C. 1, 2, 3. 1, 2, 3. Okay? And that is a totally different compound, totally different molecule, with totally different pharmacological and physiological action. Okay? So this is why we study the stereoisomers. As we can see from the chart we have in the notes, we have here. So what are the isomers? Compounds that have the same molecular formula but different in chemical structures are isomers. Okay. That's correct. So now to differentiate the types. If we have do the molecules have the same molecular formula as we have seen in the example I have shown to you now? If no, so they are not an isomers. If yes, so yes, we have an isomer now. So what type of isomers to check? The first we have, do the molecule have the same connectivity? Yes. If no, check with the notes now, please. If no, we have a constitutional isomers. So the example I have shown you before is an example of the constitutional isomers. If yes, the molecules have the same connectivity, so we have something called the stereoisomers, and we will discuss that one in details. Now, to differentiate the different types of the stereoisomers, can the compound be converted by the rotation around a single bond? Okay. If I rotate the structure, the molecule I have around the single bond, do it give me a different structure? Yes, give me a different compound, different molecule. So that means that we have, if yes, we have a conformational isomer, conformational isomers. If it is not, I have caused the rotation around the single bond and the compound stay as it is. There is no change. Okay, so we have now the configurational isomers. Configurational isomers. Now we will go deeper. Let's go deeper. If we have a tetrahedral center, do we have a tetrahedral center? Tetrahedral centers mean a chiral carbon. What is the meaning of a chiral carbon? Chiral carbon is a carbon that is attached to 4 different groups, which is attached to 4 different groups. This is the tetrahedral center, which is a characteristic of the optical isomers. Optical isomers. If not, there is no tetrahedral center, so we have a geometric isomers, as you see in the example in front of you. Going back to the optical isomers, which is very, very important topic, and I will show you now. We have 2 types now. We have the enantiomer and diastereoisomers. Enantiomers and diastereoisomers. The enantiomers have a very important characteristic. It is mirror image, non-superimposable. Check that part, which is at the far bottom right to your page. We have here the enantiomer. What's the enantiomer? It is a mirror image. If you draw a line between those 2 compounds, it is a mirror image, as if they are mirror image to each other. And non-superimposable. What means that they are non-superimposable? That the molecules are not overlapping. If you tried to push them in front of each other, the hydrogen atom will be in front of the hydrogen atom, and the methyl group will be in front of the methyl group. I will show you now. Let me check. I will draw it to you so we can, it will be easier for us. So this is the first thing, which is tetrahedral center. Tetrahedral center means that it is chiral carbon attached to 4 different groups. By the way, also, that structure is very tricky because it's not a planar structure. It is a 3D structure. Okay, it is a 3-dimensional structure. That means that just imagine that the chloride group here, it is above the screen at your face. It is vertical. Okay, it is vertical on the screen. That one is vertical. It's at your side, and the hydrogen at the bottom, at the back of the screen. It will be coming out from the back of the screen. If you can imagine that. Okay, but in an angle. It's not 100% perpendicular. It's in an angle. Okay. So if we draw a line, yes, it is a mirror image. If we try to move those two molecules near each other, it will not overlap. Why? Because the hydrogen atom here and that one will touch each other. And also the carbon here, the chloride and the chloride here. So it is non-superimposable. Okay? Non-superimposable. That's the case. That's the most important thing. It's not overlapping, meaning that the angle here, if for example the angle here is different, meaning that the hydrogen also in a structure like that, the hydrogen one here, and on the other molecule it is like this, it will be overlapping. Okay, it will be not a mirror image for sure, and they overlap, because if I move that one, the molecule, that one, like this, it will not touch the other molecule, so that there is an overlap. So we have two characters, which is mirror image. It has to be a mirror image. Consequently, it will be non-superimposable. Mean if I try to make those two molecules come near to each other, they will not touch. There will be no overlapping. Okay, so now we will go for some of the important definitions. The first definition, which is the isomers, compounds that in which all atoms are bonded in the same way but different in the space orientation. This is the stereoisomers. Stereoisomers has many divisions: optical, geometric, and conformational. So as we said that the optical isomer has to be on a tetrahedral center. What is the meaning of tetrahedral center? A chiral carbon. What is the meaning chiral carbon? A carbon that is attached to 4 different groups. 4 different groups. Let me show you how that works. We have a carbon here. That's the one. That's the carbon attached to 4 and iodine. Okay, so this is a chiral carbon, which is a carbon attached to 4 different groups. This is an exam question. What is the definition of the stereoisomers, chiral carbon, and how to calculate the possible number of isomers? Follow that equation: x equal to 2 to the power n, where n is the number of chiral carbons. So if I have 2 chiral carbon in the molecule, that means I will have 4 isomers. If I have 3 chiral carbons, in the molecule, that means I will have 8 isomers. 8 isomers. What's the definition of chiral carbon? Yes, correct, which is a carbon that is attached to 4 different groups. That's correct, 100%. Okay, so that one, the presence of the chiral carbon caused the molecule to be an optically active. What is the meaning of an optical active molecule? Optical active, if I have the active ingredient, the molecule in a test tube, and I have now a plain polarized light, and I direct it to the molecule. If I have a chiral carbon that cause the molecule, the beam of the polarized light, to have either of two directions. Either it is rotated anti-clockwise or clockwise. If it is anti-clockwise, as we see here, this is the anti-clockwise, it is levo, yeah, negative, levo negative. If it is clockwise, it is dextro and positive. That's it. So the enantiomers are optically active molecules that have the ability to deviate, to rotate the plane polarized light to the right and give me a dextro molecule. It's called dextro molecule, or to the left, it's called a levo molecule. A very important definition at that part, which is the racemic mixture. Racemic mixture is an equal amount of levo and dextro structures, molecules, sorry, equal amount, 1, 1. And the result of that mixture is an optically inactive structure, inactive molecule. So if I have an equal amount, 1 gram and 1 gram of levo and dextro molecules, that will give me something called racemic mixture, which is optically inactive, Okay. One of the most important character of the enantiomers that they have the same physical and chemical properties, but different in pharmacological action and metabolism. So the enantiomers, the optically active molecules, they have the same chemical and physical properties, but different in their biological activity and metabolism. Okay, this is very important. As I told you, this one is an exam question. Okay, now let's go to the last two parts in our section, which is the diastereoisomers. Di means two. So diastereoisomers mean that I have two chiral centers. Two chiral centers causing the molecule to be non-mirror image nor superimposable. Okay, so the molecules, if I have a diastereoisomer, it is not a mirror image and superimposable. Okay, this is the definition of the diastereoisomers. If you have two chiral carbons, so you have a diastereoisomers for sure, which is not a mirror image molecules. Now we will go for the very important part, which is the geometric isomers. It's a rigid structures. What is the meaning of rigid structure? That it is due to the presence of the double bond. It is rigid. Rigid means it's not flexible, that can flip up and down for the molecules. we have two parts, two types of the geometric isomer. One of them, which is the cis, and one of them is the trans. The cis molecule, where okay, if we have a cis molecule, that means that the groups, the functional groups at the same site. This is the one. That one is cis molecule. They are on the same site. You can write cis at the corresponding structure to a cis isomer. And if I have the functional group at the opposite direction, as you see here, that's called trans. That one must, that definition, that part must come in the exam as a definition, meaning he gives you a different type of structures and ask you which one of them is cis structure. This is one type. The second type of questions, he will give you a question which is the group. If I have a molecule that both of the groups are on the same side of the double bond, that molecule is cis, trans, levo, or dextro. Okay, so it will be if it is in the same direction on the double bond, it is a cis. If it is on the opposite direction, it is a trans. To finalize, we have at the end a structure of a product called cisplatin. It's an anti-cancer drug where the functional groups are on the same side, so it is cisplatin. Okay, that one also one of the exam questions where there is no double bond and you see the structure, just please circle on the cis. By reaching that point, we have finished the first lecture. Hope that you memorize it. I tried to combine the previous exam questions with the materials we have, so we make you bind it to the lecture to memorize easy, to study easily. See you soon on the pharmacology introduction. After we finish the pharmacology introduction, we will go to the most important thing, which is the pharmacology and chemistry of the autonomic nervous system. Hope you find the lecture useful. Hope you have written all the needed information on your notes. Be ready to the next lecture and good luck in your Kaps exam. See you soon. Bye.